Hello students, and today we're going to finish up section 11.2, which actually will be the end of chapter 11. So we're going to look at a new type of chi-squared test, but first let's go back and review our test for homogeneity with another quick example. So, oh, my dog. Oh, it's okay. It's okay, Archie. Sorry about that. My dog is now calm. Somebody delivered some treats to us, but he's fine now. So, where were we? An example. Cocaine addicts need cocaine to feel any pleasure, so perhaps giving them an antidepressant drug. I think somebody else is here now. Oh my gosh. So, giving them an antidepressant drug will help. A 3-year study with 72 chronic cocaine users compared the antidepressant drug called disipramine with lithium, which is a standard drug to treat cocaine addiction, and a placebo. So 1/3 of the subjects were randomly assigned to receive each treatment. So back in the last chapter, we would do problems where we were comparing like one drug to a placebo. But now notice we're comparing 2 different drugs with a placebo. So that gives us 3 different groups, which is a common thing that you have to do when testing a new drug. You have to compare it to one that is already in use. So then we look at how many people relapsed under the different treatments. And actually, why don't you give this one a try? Go ahead and try to write up that chi-squared test, and then press play when you're ready to check. All right, let's take a look at what you did. First, the state. You could write it in either one of these 2 ways. The null hypothesis is that P1 equals P2 equals P3. An alternative would be that at least one of the PIs are different. And then you define PI as the actual proportion of chronic cocaine users, like the ones in this experiment, who would relapse under treatment I. And because this is a test for the effectiveness of a drug, we use alpha as 0.01. Another way you could word the null alternative is that there is no difference in the relapse rate for the 3 treatments, and the alternative is that there is a difference in the relapse rate for the 3 treatments. Next, the plan. If the conditions are met, we're going to do a chi-squared test for homogeneity. We have to check conditions. The random condition is met because they're randomly assigned to treatments. Large sample size. We calculate the expected counts from the 2-way table, and we get the following. For each of them, we get 16 and 8, and both of those are at least 5. All 6 of these numbers will be 16 and 8, 16 and 8, 16 and 8. And we can use our calculator's matrices to get that as well. Then the independent condition. So the random assignment creates 3 independent groups, and if you conduct an experiment properly, knowing one subject's relapse status gives us no information about another. So individual observations are independent. So the 3 groups are independent, and individual observations are independent. Those are the 2 things you have to say. The groups are independent. The individual observations are independent. Notice we're not checking the 10% condition here because we are not sampling without replacement. This was a randomized experiment, not a random sample. Then the do portion, we calculate the test statistic. You can use your calculator, typing the observed counts into matrix A, and then it will paste the expected counts into matrix B for you. And then we get this chi-squared statistic. Showing the formula is a good idea, good way to show your work. When you give the p-value, make sure you just state the degrees of freedom that were used. So it's rows -1 times columns -1. So that's 2 times 1 is 2. The p-value gives us a p-value of 0.0052, and then that p-value is less than 0.01, so we do reject the null hypothesis. And we have sufficient evidence to conclude that the true relapse rate for these 3 treatments are not the same. Notice we are not able to reach a conclusion that one of these is necessarily better than another using this alternative hypothesis. It's just that they're not the same. If we wanted to do that, we would have to do a follow-up analysis where we look at the amount of contribution to the chi-squared statistic that each of these gives. And then we might be able to say something about this new treatment. All right, let's move on though, and we're going to look at another type of chi-squared test. So another common situation that leads us to a 2-way table is a single random sample of individuals from a single population. And then we classify those individuals according to two categorical variables. And we're looking at the relationship between the variables. So for example, if you look at a random sample of people with normal blood pressure for 4 years, and then all the individuals were free of heart disease at the beginning, and then each person took the Spielberger Trait Anger Scale test, which is a way to measure your anger or how prone a person is to sudden anger. And then you also record whether this person developed a coronary heart disease or CHD. So this includes people who had heart attacks or those who needed medical treatment for heart disease. So basically I'm studying a population of people, and thus here are the two of the variables I studied. So where they would fall on that anger test, and then whether or not they developed any coronary heart disease. So we're interested in whether angrier people tend to get heart disease more often. So we can compare the percentages of people in each category, and you can look at these percentages, and you'll notice right here, as the anger score increases, the percent of heart disease does increase. So there is a clear trend, and if you graph it, you can see that trend. As anger score increases, so does heart disease. You can see the high anger correlated with a 4.27%, moderate 2.3, and low is 1.7. So this leads us to a new chi-squared test, though. This is called a chi-squared test for association/independence. Now, we often gather data from a random sample and arrange them in a two-way table to see if two categorical variables are associated. Now, the sample data are easy to investigate. You turn them into percents and look for a relationship. Our null hypothesis is that there's no association between the two categorical variables. The alternative is that there is an association. So for the observational study with these angers and heart disease, the null hypothesis would be like this. There is no association between anger levels and heart disease in the population of people with normal blood pressure, because that's where these people came from for the study. The alternative is that there is an association between those two variables. So null hypothesis, no association. Alternative, yes, there is an association. Now, if there's no association, that means the value of one variable do not occur in common with values, not tend to occur in common with values of the other. That is, another way to word that is that they're independent. So you could also word your hypothesis this way. You could say that anger and heart disease are independent. That means the same thing as no association. Now, if you word your null hypothesis this way, that means that the alternative hypothesis would be that they are not independent. So you could do that either way. You could do null as no association, alternative as that there is, or you could say the null hypothesis is that they are independent, where the alternative is that they're not independent. Those mean the same thing. So that leads us to our chi-squared test for association and independence. The conditions are the exact same as the test for homogeneity. The way you write your null and alternative hypothesis are as we just discussed. You find your chi-squared statistic using the same formula. Let's see, the degrees of freedom are exactly the same, and the p-value is calculated in exactly the same way. So basically everything about this test is exactly the same as the test for homogeneity. The only difference is how you write your null and alternative hypothesis. So let's take a look at this test written up. So here are observed values. We haven't calculated those expected values yet, but we'll get to those in a second. Now we want to perform a test of, here are the null and alternative hypothesis we decided on. We'll use a significance level of 0.05. If conditions are met, we conduct a chi-squared test for association independence. Random, it said it was a random sample, large sample size. All expected counts are at least 5, and you can get this using your calculator's matrix, which I already did and hopefully is still saved in my calculator's memory, but I already ran the test with matrix C, and it pasted the expected counts into matrix D, and there they are. So I already did that earlier. And then the independent condition. So basically there aren't separate groups here. So basically, is knowing the values of both variables for one person going to give you meaningful information about another person? And the answer would be no. And then we are sampling without replacement, so there should be at least this many people with normal blood pressure, and that seems reasonable to assume. We then go on to the do portion. We have our calculator do this for us, and we get 16.07. If you need a review on how to do that, it's just real quick stat, test, and then towards the bottom of the list, it's option C here is a chi-squared test. I have my observed counts in matrix C, so I type that, and it's going to paste the expected counts in matrix D. And then there's the chi-squared value. Notice this is e -4. That means times 10 to the -4th. That's a really low p-value there. So you can see that p-value is very small. Definitely smaller than our alpha level of 0.05, so we reject the null hypothesis. And we can conclude that anger level and heart disease are associated in the population of people with normal blood pressure. So make sure you have that in your conclusion of what population you're talking about. And that's who we were sampling, so that's who we can make our conclusion about. Now, both of these tests use a two-way table. However, they're basically answering different questions. The homogeneity test tests whether a distribution of categorical variables is the same for each of several populations. The chi-square test for association independence tests whether two categorical variables are associated. Now, sometimes it's hard to determine what type of question you're actually trying to answer, and especially because you can sometimes word questions from this that make it sound like you should be doing this, but that's not the case. So the easiest way to decide which test to use is to look at how the data were produced. So here's the rule you should use. If the data come from two or more independent random samples or treatment groups in an experiment, use the chi-square test for homogeneity. If the data come from a single random sample, that's the only time you will use a chi-square test for association independence. So here's my flowchart to decide which chi-square test to use. And let's actually include 11.1 and 11.2 together in this. First thing you should ask yourself, am I looking at a one-way table or a two-way table? So basically, is there one categorical variable or two categorical variables? If there's one categorical variable, you use the chi-square goodness of fit test, and that's what we did in 11.1. If you have a two-way table, you then have to ask yourself another question. Does it come from a single random sample or not a single random sample? And there's kind of like two different ways we can be in this group. We could have like multiple random samples, or if it's ever an experiment with treatments, we are in this group right here. But if it is a single random sample, that is when you always use a chi-square test for association independence. If it's ever not a single random sample, and again, that could be like multiple groups, or it could be an experiment with treatments, then you use the chi-squared test for homogeneity. All right. Scary movies and fear. Are men and women equally likely to suffer lingering fear from watching scary movies as children? So researchers asked a sample of 117 college students to write narrative accounts of their exposure to scary movies. More than 1/4 of the students said that some fright symptoms are still present when they are awake. And here are the results broken down by gender and their response to that question. So here is the output table for running a chi-squared test. Now, which type of chi-squared test should you use? So this is a two-way table. So we're right here. And then is it a single random sample or not? So it says asked a sample of 117 students. So it looks like this is a single random sample. So we're going to use a test for association independence. And that's the first question here, part A. So it was a single random sample, so we use the chi-squared test for association independence. Next, there's our null hypothesis. What's the alternative? So if the null is gender and ongoing fright symptoms are independent, the alternative is that they're not independent. Which cell contributes the most? My biggest contribution is right here, males that said yes, and it looks like much fewer than expected. So I comment on that. And last, that's how you interpret the p-value in context. That should be a review. Remember, it's a conditional probability. If this, so if the null hypothesis is true, it's the probability of getting a observed result that high or higher. And so we lack evidence to conclude because the p-value isn't lower than 0.01. So that's it for this lesson. Send me any questions you have.